Hi, everybody. Good afternoon. Well, today we're going to be discussing challenges in building RAG systems, the kind that combines retrieval with generation to ground LLMs in reality and your external data. You see, RAG usually sounds easy on paper, but teams often hit complexity in areas like hallucination control, latency, and retrieval quality. We're going to discuss what challenges they face and what you can do to fix them. Okay, so this doesn't work. I think I'll just do it. Okay, a quick primer. Let's look at what RAG is to begin with. You see, LLMs have a fixed knowledge cutoff. I'm sure all of you have experienced it, right? So they do not have access to new, evolving, or latest information. In fact, not even private information. So what do? Well, that makes them really unsuitable for a lot of real-life scenarios. These simply supplying context, which we do pretty often as developers, doesn't scale a lot either, because then you run into issues like contextual window size limits, right? So you run into issues like you have to do relevance filtering manually, and as the size of this input grows, the quality of the system degrades. I'm sure you've experienced that as well. That is where RAG comes in. RAG tries to solve these problems at scale. Essentially, the way it works is you use a user's query to match the most relevant documents from your knowledge base. You extract those and try to find answers within that document set. So we're going to discuss, like I said, we're going to discuss the challenges. But first, let's quickly also look into the architecture of a typical RAG system. Can I get a show of hands? How many of you are aware of this? It's a quick show of hands. OK, cool. Good to know that. It starts, I'm going to give a quick primer for the benefit of those who don't. So it starts with the user query, and user query is converted. User fires a query. You have a question, you fire a query to the system. It's converted into, there's an embedding model which converts the user query into query embeddings. You use these embeddings to search the information, search the right documents in the knowledge base. You filter out, you actually pull up the documents that are there in the criteria. And then you try to filter top K documents out of the fetch documents based on a similarity score. Then what you do is you have these top K documents, you have a user query, you put them together, serve it to the LLM, and the LLM gives you the response. That's how a typical RAG system works. Now the question is, where does OpenSearch figure in all this equation? Well, it sits in here at the retrieval step. That's right after a user's query is embedded. So it sits in at the retrieval step. And at this stage, what we try to do is we try to find relevant documents against a query match. And the way we do it is, like I said, we embed the user's query, and that is we try to match it with a pre-calculated set of document embeddings. It's a large set of document embeddings, and that's where OpenSearch shines. What OpenSearch does is think of OpenSearch as a large vector store. It saves all of these document embeddings. And it also acts as a very powerful and fast semantic search engine, a sort of a similarity search engine using its KNN plugin. So OpenSearch is the heart. I mean, it literally is the closest to the heart of the system. So this system would not work without OpenSearch. So the kind of when you venture into building these systems, the kind of issues, the kind of roadblocks you face are multifaceted. The problems are around quality, around cost, around safety, around knowledge. Quality is the biggest hurdles of all of these. And today I'm going to discuss quality in detail. I wish I had more time, but such is life. OK, so this insight is, OK, so it's not pretty visible here, but this is the performance quality index. So LangChain, have some of you used LangChain? Yeah. So LangChain came out with the State of AI Agent report, and they surveyed over 1,300 professionals. And what they found was over 41% of those folks indicated quality being the biggest challenge in building these systems. There are a lot of other surveys and publications as well that point to the same, like similar number, but you get the idea. Quality is the biggest hurdle. I'm sure those of you who have even ventured into implementing these systems, that's the first thing you run into, the quality of these systems. Why is quality so hard to get right in RAG systems? Well, it's because it's hard because of multiple data-related challenges to begin with. So we're going to discuss the challenges of data curation. We're going to discuss the challenges in the precision versus recall. We're going to discuss semantic gap-related challenges. And we're going to discuss irrelevant retrievals, all of this in detail. These are not the only quality-related challenges. I've filtered out some so I can talk about it in this limited time, but let's talk about these, all of these. Data curation is one of the hardest problems that you'll encounter when you set out to build these systems. Why is it hard? Multiple factors. Again, these are just some. There are a lot more, but some of these are, the first one I'm going to discuss is format diversity. You see, your source data lives in a lot of different formats: PDFs, HTMLs, Word documents, spreadsheets, right? It's sometimes in emails and a lot of other internal tools as well. Each of these formats have their quirks, and it's extracting a clean and consistent data from all these different formats is beyond trivial. Those of you who have tried would know that. That's the problem with format diversity. A lot of different formats, everything has its quirks, difficult to get everything right. Noise and redundancy. Documents are noisy. Have you seen, like, when you go on to parse these documents for AI agents, like, documents have headers, they have footers, they have disclaimers, they have a lot of irrelevant sections. And if you don't filter out those sections, you're going to be polluting your vector indexes, and that's going to lead to subpar results. And then as content structuring, having clean data is not sufficient. How you chunk this data is super important as well. If you create larger chunks out of your documents, they're semantically imprecise because they have a lot of information in one chunk. And if you create smaller chunks, imagine what would happen. You would essentially lose context from these chunks, right? I see a lot of people nodding their heads. Good to know that a lot of people are given a shot to this. Interesting. Then it's freshness and updates. Your data is never static. Think about your product documentation. Think about support docs. Think about your product specs. Think about your privacy policies. Everything keeps changing and evolving, right? And so the thing is, maintaining this freshness in your data indexes and maintaining it automatically is, again, not a simple problem to solve. And if you have to do that to maintain the quality of your system with these evolving documents. Next problem, which plagues the quality of these RAG systems, is called precision versus recall. Again, very common issue. Both of these are important. I'm going to discuss what precision and recall is in a moment, but both of these are important. And optimizing one comes at the cost of the other. That's a sad part here. Precision is fetching the most relevant documents out of the database. And you would imagine it's good, right? The most relevant documents. The LLM is happy. It gets the right context. It's able to generate answers. All hunky-dory. Life's good. But you overdo precision, you're missing out on the peripheral parts of the answer. That's a problem with precision, overdoing precision. And that's where recall comes in. Recall means extracting like loosely related documents from the database, like sort of peripheral information to the answer. And that's good because that helps in completeness of your answer. But the problem with that is you overdo that and you're supplying a lot of irrelevant context to the LLMs. So that's where the problem between, there's always a tug of war sort of between precision and recall. It's hard to get this balance right. The third problem plaguing these systems is semantic gap. Interestingly, the way we users phrase query is very different from how information is saved in these databases. Imagine the last time you did a Google query. We write very vague queries. We just expect that the system would know the answer. Like they would know what we're trying to think and imagine, and they just know. So we write very vague queries, and that is not how information is saved in these knowledge bases. And that makes it tricky for these systems to pull out the answers. But let me give you an example. The query I fired is, why are certain deals missing in the pipeline? This is a CRM. I'm talking about a CRM system here. Why are certain deals missing in the pipeline? It pulled up certain documents. This is the documents that, and this, by the way, I did a small POC for the sake of this presentation. So this is a real life example. So it pulled up certain documents, and the answer it generated is, listen to this carefully. Answer generated was, you can use filters on your dashboard to sort of control what deals show up in the dashboard, right? Now that's a poor answer. Why? Let's discuss that. It's a poor answer because what it did is, remember my query? It sort of used these keywords like pipeline, report, missing, deals. It matched them semantically with the information in the database and tried to pull out whatever irrelevant documents it could and gave me that answer. It missed out important pieces. Look at this is actual answer. Some deals could be missing because they are in archived pipelines. Some deals could be missing because they don't have the right fields to show up on a report. Some deals are missing because user doesn't even have permissions to see those reports, to access those reports. So this is the right answer, but what it gave me is use filters. I mean, it's one part of the answer, but it's not the entire answer, right? So it gave me that answer. Now, so it sort of generated this. Sorry, just one second. I'm trying to pull up one more information. Okay, I think I missed that. Anyways, so it sort of pulled up these, and notice how in these documents, these concepts were not even present in the documents, like archive pipeline and all. This wasn't even present, right? So what do you think the answer is going to be? Obviously, the vague answer that it gave me. Another problem facing these, plaguing these systems is irrelevant retrieval. Again, a simple example. The query that I fired to the system is, how to file a provisional patent. I was trying to find out some information on that. And it gave me all sorts of irrelevant results. Look at the top results. Top 10 lawyers near you. Why startups fail? Super irrelevant to my question. But the real answer was there in the database. I can assure you of that. But why didn't it pull up that answer? Why did it pull up these documents? Well, that's because the phrase provisional patent exists in these documents with a much higher frequency than it does in the document that actually contained my answer, right? So all of these challenges make, they plague the quality of these systems, essentially. Now that we've discussed a bunch of these different challenges you face while building these systems, let's discuss some possibilities. Let's discuss some solutions that will help you make these systems better. Well, the first one, sorry, I forgot to mention that. We're going to discuss solutions impacting the problems like semantic gap and irrelevant retrieval. I'm not going to discuss the other ones, precision versus recall and data curation. I'm not going to discuss that here. Again, time constraints. So one of the techniques that can help you solve the semantic query gap is called query transformation. It sort of rephrases, it converts a user's query into semantically richer and more aligned variants. How does it do that? Because the LLM understands the concept. When it sees this query, it understands the context, that it's fired in the context of a CRM system. So it's going to generate much more relevant queries knowing the context. Instead of the user query, it's going to generate a lot of other variants of the query, and you fire these variants together to get the right answer. Notice how you have archived, closed, permissions, etc., all of that in the rephrased queries that the LLM generated. So that's one thing that can help you, and in fact, Microsoft recently benchmarked this technique. So across various query types, concepts, facts, keywords, questions, the different query types they used, across all of these query types, query optimization had a profound impact on the quality of the system. So they paired query transformation with a technique called search re-ranking, did it together, and the results they found were pretty promising. There's a scale on which you measure the correctness of the system. It's called NDCG. There are many such scales. One of them is called NDCG. On that scale, Microsoft proved that they got like an uptick of 26% on an NDCG scale, 26 points, and that is significant. Another interesting approach which can help you solve the problem of semantic gap is called HYDE. It stands for hypothetical document embeddings. And the way that it works is, it's actually a very simple concept, very powerful. The way it works is, instead of embedding the user's query and using that to search the documents, we ask the LLM to generate a hypothetical answer to a query. So remember, I'll talk about an example here in a moment, but we generate a hypothetical answer to a query, and we embed that hypothetical answer to find the relevant documents in the database. So why does this help? This helps because users' queries are very vague, like I discussed earlier, very vague queries. And what happens is when you ask the LLM to generate a hypothetical answer instead, it understands the context of the query. So it generates those hypothetical answers with relevant, domain-relevant concepts. And when you use that to search, the probability of you finding the relevant documents increases multifold. And I'm going to show you an example here. Look at this. Oh, by the way, just quick thing. This is where HYDE sits in the RAG pipeline. It sits in right after the user query is fired. We ask the LLM to generate a hypothetical answer instead of finding the documents. So here's the same query. I'm revisiting the same query. Why are certain deals missing from my pipeline? Now, I did not look for the answer in the knowledge base. I don't care about it at this stage. What I did is I asked the LLM, hey, why do you think some deals are missing from my pipeline? What it did is it generated a hypothetical answer. Again, it understands the context of the query, generated an answer with domain-relevant concepts. Look at this is again a real-life example I tried for the sake of this presentation. It generated a hypothetical answer with filters, visibility settings, and permissions. It did encapsulate some of these concepts. Now, when I embed this query and use it to search for the relevant documents, I am going to hit more results, more relevant results. Look at it hit report filters, it hit user permission, but it still missed some of these, archive pipelines and custom field exclusion. So it missed some, but it got more than what a regular query would have got me. So that's kind of the interesting thing. So now again, there's a study called Advanced RAG Output Grading Study. It was done by researchers in June of 2024. And again, what they found was interesting, that They did multiple runs, I think thousands of runs across each run, like on an average, sorry, not across each run. On an average, what they found was a 10% uptick in the precision of the systems that used hide approach versus a naive RAG. So again, pretty promising. And now let's move on to irrelevant retrievals. Remember I said I'm going to discuss solutions to two problems, semantic gap and irrelevant retrievals. So let's look at irrelevant retrievals. The reason why you get irrelevant documents in the result, one of the reasons, sorry, is that documents are noisy and the surface area across which these RAG systems operate, the sheer length and breadth of the knowledge base, it's huge. So it dilutes the quality of results you get. If you could somehow filter these documents first, let's say you could narrow down the set of documents to search from, the results you would get would be phenomenally better. And one way to do that is, when you embed your documents into a data store like OpenSearch, you add a metadata along with the data. So so this is actual content, these are the embeddings. You add some sort of metadata depending on your domain. And then when you fire a query, first filter the documents from the entire knowledge base based on some of these filters, and then on the filtered documents, run an embedding-based retrieval. Again, an example, let's say you're keeping a data store of fiscal documents of a company, right? Oh, no, sorry, fiscal earning reports of a company. Now you're keeping earning reports. Now you need to find some information on those earning reports, right? Now, mostly, a lot of times what happens is you want to find for a certain year, not the entire length, like age of the company, obviously, right? So what you do is you filter these documents in the database based on fiscal year first, and then you run embedding-based search. This will give you much better results than just blindly shooting a query in the database. Another reason why a lot of these irrelevant retrievals happen is because individual chunks, they do not have sufficient context in them for effective retrieval. Let me give you an example. I fired a query, again, a vague one, Nike, so this query was more around, yeah, this was Nike, yeah. So this query, this example I did was for Nike. So Nike climate change report. Now look at the chunk. Look at the chunk on the slide. It does have climate change. It does discuss climate change impact, but it doesn't have Nike anywhere. So when the retriever goes to retrieve this chunk, it retrieved it with a similarity score of 0.1. For those who don't know, 0 is the lowest, 1 is the best, and it retrieved this chunk with a similarity of 0.1, which is pretty poor. But this is actually the answer. It doesn't have Nike, so it doesn't know whether this is the right answer. So it retrieved it with a similarity score of 0.1. A way to mitigate these problems is you take, with the chunk text, you add a chunk header and embed these together. And in this example, what I did is all that I did is to the chunk text, I added a chunk header, which is nothing but the title of the document from which this chunk was created. The moment I did that, it bumped up the similarity score to 0.9. Like from 0.1 to 0.9, that is a drastic change in quality. This kind of technique is called CCH. It stands for contextual chunk headers. So we're going to talk about the benchmarks here as well. They did a benchmarking across many different data sets. They did across 100 AI papers. They did benchmarking of CCH against Besemir's financial data of Besemir cloud companies. They took up a source graph as a company, so they took up their company policies, the publicly available policies. They did benchmarking on that. They did benchmarking on, this is US Supreme Court's, not India's, US Supreme Court 2022 opinions. They did all of this benchmarking based on that. And again, what they found was pretty promising with CCH. Just one technique alone, the kind of results you got in terms of precision were 26% better than without CCH. So again, very promising. Well, if you like the presentation today and you want to dig in further, I would urge you to try out some of these techniques. At least start reading about them, see if they. So the first one is called RankRag, then it's Raptor, then it's GraphRag. You can find a lot of information on these on the internet. They're very pretty sophisticated approaches. The problem is, the only small caveat that I'm going to add here is, people have tried these techniques, but the feedback has been sort of a mixed bag. For some it worked, for some it didn't. So what I'm going to urge you is, if you're going to try these techniques, you're going to need a lot of experimentation and tuning to get it right for your use cases, right? So yeah, with caution, try this with caution. And look, I understand, I built a lot of RAG systems. I can tell you RAGs are messy because data is noisy, LLMs are unpredictable, and the integrations are extremely painful. But once you get this right, it's completely worth it. Like, it helps you build a system that's not only smart sounding, but grounded in reality and sort of your documents, right? Not just hallucinating on other stuff. So this RAG systems, building RAG systems, helps you not just make your systems powerful, it sort of is the need of the hour. It gives you a competitive edge. It gives your companies a competitive edge that not many others have. So yeah, thank you for listening to me, and I hope you liked the presentation. And I'm not going to keep you waiting for lunch.